What is up? Assignment 2, LONCAPA, child drowning. Let's do it. Okay, so first things first. Child is drowning. Let's assume the child is here. We'll draw it out. And it's being pushed by current. That will say is it's the velocity of the water to the ground. So that's his speed, because he's just moving with the same speed as the current. And then the child is 0.505 kilometers from shore. 0.505 kilometers and 0.765 kilometers upstream of a boat landing when the rescue boat sails out. So this is up, this is downstream. So our good old boat is like there-ish. And our boat is trying to head to the child. Well, trying to meet up with the child. So we'll have two things here. We'll have one, the velocity of the boat to the ground, and two, the velocity of the boat to the water. And we established that it is 0.765 kilometers from the kid. So if we're taking into account the kid drowning, moving down the river, then the angle we have to aim our boat would be that angle there. But they gave the relative speed to the water. So the velocity of the boat relative to the water is 19.7, and the velocity of the kid relative to the water is actually 0. So here we have, we'll call this angle theta for now. So we can find our theta with the values they gave. So our theta equals opposite over adjacent, right? 505 divided by 0.765, which equals, and let's put this into the calculator, 505.765, and we end up with 33.4 degrees. So the first question, what heading relative to the shore should the captain take? That's our answer to the first one. He should take that heading relative to the shore. Okay, so on to the next, where we want to find now what angle in degrees does the velocity of the boat make to the shore. And the velocity of the boat, we'll call this angle here, we'll call it alpha. The velocity of the boat is alpha plus theta. So that's what we're trying to find. Thing is though, with our z rule, we know that this means that up here as well is also theta. Which means we have as well the velocity of the water to the ground is 2.5 kilometers per hour, and the velocity of the boat to the water is 19.7 kilometers per hour. So what do we see here? We see cosine law. So we have our velocity of the boat to the ground squared equals velocity of the water to the ground squared plus velocity of the boat to the water squared minus 2 AB cos theta. And I am too lazy to plug that in, so we'll do a cosine law thing here. So we'll do 2.5, 19.7, and the theta we found was the one from the previous one. So we have the velocity of the boat to the ground is equal to 17.67. Okay. So we have this here. And let's clarify that it's kilometers per hour. So now that we have that, we can use our sine law to find alpha. So we have sine of alpha, and its opposite angle is 2.5. The 2.5 kilometers per hour is equal to sine of our theta there, our theta which was 33.4, over our newfound side. So sine, or I'll just do it all in one shot, and we find that alpha is equal to sine of it. Alpha is equal to 4.47 degrees. Okay? So now what we wanted to find for question B here, so I'll label as well. That was A, this is now B. So for question B here, what we were trying to find was theta plus alpha, which was equal to 4.47 plus our theta, which is 3.4, which is equal to 4.47 plus 33.4, 33.9 degrees. So that is our answer to B. That's the angle in degrees the velocity will be making with the shore. Now we want to move on to find C. We'll do it on the left here. So, how long does it take the boat to reach the child? So how long, we know that time is equal to distance over velocity, right? But what distance and what velocity are we looking at? Well, in this case, if we look at velocity of the boat relative to the water, we can make this triangle here that I'll redraw because things got too hectic up there, where we have the distance from the child and the boat's velocity relative to the water. And we can use this triangle to find our distance, and we already have our velocity here as well. And this works because the child, if we're referencing to the water, remember the child has no velocity. So in reference to the water, the child stays at that one spot. So here, we can do time is equal to, and that's just Pythagorean theorem, plus 0.505 squared. All of that over the velocity of the boat to the water, we remember is 19.7. So now it's up to plugging it in. So we have root of that squared plus 5.05 squared, all of that over 19.7. And that gives us 0.0465. And remember, we were working in hours, so hours. And if you wanted minutes, times by 60, and we get 2.75 or 79 minutes. And that would be your final answer to question C.